Out to school by foot on a fine spring day, or distance from school in blocks is given in as a function of the time in minutes she has been walking. The function is represented by the graph given below. So what they're telling us in the little setup here is that the x value is representing time, and the y equals f of x value is representing distance in blocks. All right, so x, y, under normal circumstances, but they did say it's given as a function of time. All right, so we know that we're looking at a y equals f of x situation. All right, so the first question is pretty basic. How far does Erica start off from school? But yeah, we got to understand that we're trying to work towards being able to interpret this using the appropriate notation. All right, so we don't just want the answer, we want to state it using the appropriate notation, because that's what the expectation is going to be. All right, so how far does she start off from school? Well, that's talking about, well, if she hasn't left her home yet, and I'm assuming that it's some reference to home to school, but I guess it could be some arbitrary location. She's 22 blocks away, because at the instance when no time has passed, she hasn't gone anywhere, so that would be her initial distance. But in terms of notation, so you can pull that right off the graph, and if it's a multiple choice question, that might be fine. But in terms of having the appropriate notation, what we would say is f of 0, y is equal to that f of 0, which is equal to 22 blocks. All right, because the x value is the time, writing f of that x value is saying we're plugging that x value into the function and making a determination of what the y value is. All right, the notation gets that whole idea across. All right, same idea for number 2. What's her distance from school after she has been walking for 4 minutes? That's saying y equals f of 4, because they're giving us the time. On the graph, that corresponds with this point, which has a value of 14. So 14 blocks. All right. But then number 3 is kind of different. And I also want to change that a little bit. It says subway pass. There's really no reference to a subway in this whole problem, so I'm going to change that to look for her homework. And actually, I'm going to get rid of number 4 completely, because that's another reference to a subway. The whole subway thing kind of comes out of nowhere. So another slight adjustment to number 5, just so you're aware. All right, so after walking for 6 minutes, she's thinking and walking as she goes, and she's like, oh, did I pack my homework? So she stops, has a look in her backpack, taking a look to see if her homework's there. We're just asking how long did it take for that to happen. All right, so the instant in which she stops moving, all right, so time is elapsing, but there is no movement happening. It seems to be over in this interval here. All right, that's going from 6 to 9. All right, so the way we would write that notation-wise would be to say that at f, or for f of 6, we have a result of 10, y equals f of 6, y equals f of 9. We also have a 10. These values are the same. There's no change. Everything in between is also the same. All right? So then I would say 9 minus 6 is equal to 3 minutes. All right? I'm going to scooch this over. I'm just going to put a little note here, just saying that there's no change. That's not something you'd have to write, but I just figured it would be a good idea to indicate it here. All right, there's no change in the distance traveled over those 3 minutes. Now, it is possible that you could find over an interval no change and it still be the wrong answer, because it's you could have something like this, from 6 to 9. The values are the same, but there's a lot of crazy stuff going on in between. That's not what happened here, though, and I'll get into why that makes sense in this instance, but that's kind of part of today's lesson, where we get into the slope over an interval and how that impacts the interpretation. So more on that later. And then number 5, well, which is now really number 4. How long did it take for her to get to school? Well, she's at school when her distance away from school is equal to 0. So we're really asking, when is y equals f of x equal to 0? All right. In the form of an equation, what you would write is, you define variables, but I would say a typical variable that we've been using is n. So we would say let n equal the number of minutes so we could say f of n is equal to 0, and then solve for n. That's assuming we had an equation. All right. Notation-wise, that would make sense. We've done that before. We even used the Desmos to figure that out. So if we had equations for this, that might be something I would do, like create a slider, figure out the n value that gives an f of n equal to 0. But here it's really just saying, all right, well, if f of n is the y values, or f of x is the y values, then I'm just looking for the instance at which the y values are equal to 0. That happens on the x-axis, and it happens at this location, distance from school equal to 0. All right, so at n is equal to 15 minutes. All right, you can see here that in every one of these instances, you could have come up with the answer just by looking at the graph without writing any of this notation, but the whole point is to learn the notation. All right, so that's kind of why we're here. This is really, honestly, not, it never comes out the right way when I say it, but this is really kind of a middle school type problem. Maybe even like late elementary school type problem. You give this question to somebody and say, okay, tell me what's going on here. You might say, how far away from school are you? How long did it take to get to school? Stuff like that. You just pull it out of the graph. We're here to learn about the notation. All right. And we're using something that's pretty easy to solve without the notation to verify that we're doing things right. All right. So it's kind of weird. Like, the lesson's called Interpreting Graphs, but it kind of feels like we just did that. There's other things, other characteristics of graphs that we have to get into, like whether a graph is positive or negative. All right. Now, when they say a graph is positive or negative, they're referring to the y equals f of x values. All right. So it's refers to y equals f of x values. All right. And you can see the little diagram there. Positive is above the x-axis. So actually, I kind of steal my own thunder. It says the positive regions of a function are those intervals where the function is above the x-axis. It's where the y values are positive. Negative regions are below the x-axis, below. It's where the y values are negative. All right, it seems to be a pretty simple process. Oh, not even process, just concept. The process itself is a little bit more complicated because what we have to do, when you see the examples on what intervals is the function positive, it's asking us, and it's kind of a strange, overly worded explanation, but overly wordy, for which values of x are the y equals f of x values above the x-axis. All right, so for which values of x are the y equals f of x values above the x-axis? Same idea for negative, except below the x-axis. All right, so I could just do a quick copy-paste job there. Let me do a little shrinky dinky here. All right, but this is asking us for intervals, is asking for domain. All right, so when I look at the graph, I can identify the parts that are above the axis and the parts that are below. I could also identify the part that's on the x-axis. That's actually going to be your irrelevant value. So here's a value that's on the x-axis, right at -1. I'm going to put an open circle there. It's kind of hard to see the open circle, so I'm going to fill it in with white. There we go. All right. The part that's above the x-axis just crashed. Lovely. You can do it. It's a turkey. I gotta find the notebook. There we are. So the part that's above the x-axis is right here. The part that's below the x-axis is right here. I just have to state for which x values this is happening. All right. Well, they both have arrows on their extreme points. So this one is going to go on forever to the right and up. All right, so it's going to go on forever to the right. It's going to go on forever in the upward direction. All right. I care more about the right because we're stating the x values. All right. So if it goes on forever to the right, it's going on to positive infinity. All right. So the whole idea of domain talks about starting and stopping. Where does it start? Where does it stop? All right. I also did that. I think I showed it to you all, that animation that I made where you have some kind of graph and you're looking to determine the domain. You're looking at the graph as if you were standing on the x-axis and looking up at the graph itself. All right. What part of the x-axis would you be covering, based off of the graph that you create? All right, so that's what's happening here. I'm just looking at it from the perspective of the x-axis and saying, all right, well, what part of the graph is being mapped onto the x-axis? Right? It looks like anything from -1 right on down to infinity. All right, so anything from here to here and everything in between. That would get me above the x-axis. So I would say, because there's no solid point at -1 relevant to the positive set of values for y, so I put the open circle there because it's excluded from the set, we would say above -1, so greater than -1, and out to infinity. And we can never include infinity because infinity is always on the move. Right? Can't capture it if it can always get away. It's elusive. All right. Now, the red part of the graph seems to be going down forever and also to the left forever. Left forever is where negative infinity can be found. A little lighter on the green. All right, so my start and stop here would be negative infinity to -1 and everything in between. All right, so negative infinity to -1 would cover the domain of the part of the graph that's negative. All right. The only number from negative infinity to infinity that's not going to be included here is -1, because that's the only number that's neither positive nor negative. That has a value of 0. All right. Now, increasing, decreasing, and constant, it's not in the title, but constant we'll be discussing also. A function is increasing if as x increases, y increases. All right, slope is positive. Goes uphill. All right, we're reading these graphs when we're evaluating slope. We're reading the graphs from left to right. So anything that's going uphill would be considered uphill, but only from the perspective of left to right, as if you were reading, like reading a book, reading words on a page. All right. If a function is decreasing, that means if x increases, then y decreases. All right, slope is negative. And that one's going to go downhill. And then you have the constant situation. If something is constant, it means it's not changing. All right? So if x increases, decreases, does a dance, sings a song, doesn't matter, y is going to remain exactly as it is. It's not going to change. All right? All right. Slope is 0. And you have some kind of plateau, assuming I spelled plateau correctly. Pretty sure I did. I feel good about it. I mean, my E looks pretty funky. Like it's an oversized E. So it's making it look like I spelled it incorrectly, but I'm feeling pretty good about the spelling. Plateau, tableau, Darno, former New York Mets catcher. Always injured. and goes to the Braves, wins the World Series. Braves won the World Series, right? Actually, I have no idea. Once the Mets are eliminated, usually in like June, I stop paying attention to things. On what interval is the function increasing? All right, so we look at the picture. We're just looking to see where it's going uphill from left to right. You read the graph from left to right, left side to right side. Where is it going uphill? It's not, and this is something you got to be careful about. Don't get fooled by the arrows. Just because this arrow is pointing upward doesn't mean that you are going uphill on this path. That path extends uphill. But you're traveling on that path. If you're going from left to right, you're going downhill. All right. So I like going with a skiing analogy, just because that's what I relate to. So if this is a mountain, the path or the trail extends. We could say forever up in this direction, but to make it sound more practical, I would say it kind of seems like it goes forever. Like if you're a skier, especially if you're kind of new to the sport, sometimes you look at a mountain and you're like, wait, how far up does that go? I got to go down that? I got to rethink this. But then you get on it and you ski. I always have anybody that I'm teaching to ski for I never take like beginners up, but people who have a little bit of experience but haven't gone up the mountain, I'll take them up. They have the skills, they just haven't put it to the test yet. They look at the mountain and they're like, oh my God, it seems to go up into space. That's what we're talking about here. All right. But I think if you're a skier, or snowboarder, you probably have done this at one point where you've worked your way down a trail or down a really steep slope without realizing how steep it was. And then you turn back and you look and you're like, whoa. It's like a wall. It's like I just skied down that. And you look and you see what you just accomplished. You feel like $1 million. It's kind of cool. And by kinda, I mean it's awesome. See you on the slopes. But I use my Gore Mountain analogy. It doesn't always work, especially if you've never been there. Then it definitely doesn't work. But Gore Mountain has, and also Stratton, if you've been there, they have mid-mountain lifts. And a lot of mountains have this too, where you ski up. I'm sorry, ski up. Jeez, strike that from the record. You take the chairlift or the gondola up, then you ski down. You don't go all the way down. You go to the mid-mountain lift, and that takes you up to the tippy top of the mountain. All right. So that's kind of this. So if you're skiing downward, you'd come down, and then maybe you'd hit that mid-mountain lift again, and then go up to the top of another mountain, and then ski down the rest of the way. All right. So the uphill, downhill part of it, you don't have to be a skier to understand that. Driving in a car, walking, walking up and down hills, like it's a pretty basic concept, but it's very often and easily confused when you start mixing ideas together. It's very often and easily confused with the whole positive negative thing. All right, positive is above the x-axis, negative is below the x-axis. Increasing kind of feels like positive. All right, but it's talking about something else. It's talking about the slope. All right. So where is it increasing? We look at the start and the stop in terms of the x values. It's starting, it's stopping, and it's covering all the values in between. So it's going from 0 to 2, brackets all around, because those are solid points included in the interval of increasing. Now, this is a slight deviation. Actually, it's a massive conceptual deviation from what we were doing for positive, negative, but it's also slight in terms of the notation. These get brackets because it's not an instance where these endpoints are neither increasing nor decreasing. They're considered both the endpoint for where the function is decreasing and also the starting point for where the interval or the function is increasing. All right, so whereas for positive negative, there's an interval where, or there are values where it's neither. Here, there are values where it's considered both. Right, so they have to be included. All right, so that could be kind of confusing. Now this graph is going to go forever to the left. It's going to go forever up. Make that look more like an up. Forever to the right. Forever down. All right, so forever to the left is at negative infinity, or it brings us to the direction of negative infinity. Forever to the right gets us to positive infinity. So if I'm discussing x values for which the function is decreasing, my start would be at negative infinity. My stop would be at 0. So negative infinity to 0. Oh, bracket on negative infinity. Noob. Negative infinity parentheses 0. And then going from 2, that's my first or my second start, going to infinity. But I have two distinct intervals that need to be united to make up the set of values that represent decreasing decreasing y values for this function. So I would put a u here, u for union. All right, and we get into what are called, well, they call them maximum minimums, but there are other names for these things, and unfortunately there's a lot of names. So we have vertex or vertices. So vertices, and I'll say singular vertex, or extrema. Singular for that would be extremum. So you might see maximum, minimum, vertex, extremum, vertices, or extrema, any of those words. All right. So when we talk about extreme values or maximum, minimum values, we're talking about that transition point. We actually just talked about it. Those points that are both part of the interval of increasing and decreasing, that transition from increasing to decreasing, that's a maximum. The transition from decreasing to increasing, that's a minimum, as you read the graph from left to right. So it's pretty easy to pick them out because it's really just some kind of turning point in the graph. If it's a turning point on the low side, like a valley, then it's a minimum. If it's a turning point on the high side, then it's a maximum. We call them relative versus absolute, depending on the situation, because it can be a relative maximum, as in it's a turning point, but it might not be the highest value in the entire graph, right? The highest y value. It just might be the highest value compared to the individual values surrounding it, right? So like, for example, this is a relative maximum. It's a maximum point compared to the points that immediately surround it. But since this part of the graph goes on to infinity, there are going to be some y values that are way bigger than this y value, way bigger than 3. But, you know, comparatively speaking, this y value is pretty big compared to these other values. All right, so we got the little peaks and valleys. So you're looking at like, I used to use analogies like monarchies and stuff like that. I never know what's appropriate anymore, but I think it's fine. You know, you got like the the lords, like the earls, the dukes, and then you have like the king or the queen. All right, so you look at the absolute maximum as being the highest of the high. All right, but you still have like the little rulers. You still got like the dukes and the oh, what are they? The duchesses, right? You still have those individuals. They're like lower level. In video game world, you have like the bosses, on each level. But then you have like the one that you got to beat to win the game, So, Bowser or whatever. I mean, it's a little old reference, but you get the idea. Shang Tsung. Who's the other one? I can never remember. There was two of them. There was Goro. Whatever. Anyway, so we have the relative max. Sports analogy. Like you got semifinals, finals, you got playoffs, right? You win a playoff game, you're like champion for a day, right? But then you got to win the next one in order to win like the Super Bowl or the World Series, right? So the World Series would be the absolute. Each one of those individual playoff wins would be the relative extremum. All right. So name a relative minimum of this function. Well, the coordinates of the relative minimum would be at 0, -1. But the relative minimum would be just a -1. We'd also write that as f of 0 is equal to -1. All right, the relative maximum, 2, 3, with just the 3 being the relative maximum. Or we would write it as f of 2 is equal to 3. All right, so that's usually an easy one to identify visually. You can look at it and say, okay, well this is the little peak, this is the little valley. That's easy enough to identify. The things that people usually get confused are positive, negative versus increasing, decreasing. All right. So if you can focus your time and energy on mastering that, just kind of memorizing that, you'll be in good shape. Because end behavior is another straightforward one, because it's one of those terms that really defines itself. End behavior. How does it behave at its ends? All right. Well, its ends would be as x is going to infinity, or if x is going to negative infinity. Right? Negative infinity is over here. That would be one end of the graph. The other end of the graph would be over here at positive infinity. We would want to know where y equals f of x is going. And we've done this a bunch of times, where I'd say, okay, if I go to the left, following this graph, where am I going? I'm also going up. All right, well, where's up going to take me to? It's going to take me to positive infinity. All right, so as x goes to negative infinity, y goes to positive infinity. If I go forever to the right, where am I going? It looks like I'm going down. Following that graph, it looks like I'd be going down forever. All right, down forever would bring you, if you could get there, to negative infinity. And so that would be my end behavior. It's infinite in both regards. It's just a question of what kind of infinity. If it's going up, it's going to positive infinity. If it's going down, it's going to negative infinity. And that's really all there is to it. All right.